Welcome back, Code Websters. Today we're going to be finishing our new view-based linear regression system. So, as we showed last time, we got the basic setup running and we got the charts running. And this week we're actually going to finish off the actual linear regression part. But before we go down that route, I want to actually explain a bit about linear regression and generally about machine learning as a whole. The basics for linear regression is that what we're trying to do is trying to get a line of fit that approximates all our data points. So to do that, we are essentially going to try to minimize the error. And the error here is simply the difference between the data points and the line of fit. So here the error might be 5, the error might be 10, error might be 10. And then overall, we're looking at, hey, if I add up all these errors, how can I keep reducing it and make a line of best fit? But essentially, in this line of best fit, it might not be fitting all the data points, but this is the best way to minimize most of the error, to try to get all the data points close enough. Mathematically, today we're going to do a bit of math, so try to hold on to your seats, boys and girls. So the general function we're using for our linear regression is mx plus c. Essentially here it says h is a function of x, m, and c. We normally use h because h is hypothesis, and so this is normally known as hypothesis function. Now, as I explained before, the error is essentially the difference between our data points and our actual line of best fit. This mathematically is displayed as, hey, y of the x point minus h of the x point. We square that to get rid of any negatives that we're using, and we just half it because of some mathematical elegance, which I'll show you down below. This is the E minor error. This will give you negatives. So this essentially what will most likely oscillate to 0. It's kind of useless, but I just like showing it. Now we're going to actually talk about something called gradient descent. So let's say I put a random line of best fit because we normally choose our M and C values to be random. How can I actually get this line to be, or approximate to be, the best line of best fit and try to reduce the error as much as I can? All right. So let's say we have this parabolic function. Probably don't have it, and this would be really rare, but if we did, we essentially want to try to get to a global minimum. In calculus, to get to global minimum, we basically use something called derivatives. Using derivatives, we found that the best way to actually get all our values to go to the minimum is actually minusing it by the actual derivative. All right, so this will be explained a bit more in maths. I've given you a bit of description in the actual docs. So if you look in the description of my YouTube channel, you should find probably some extra information talking about derivatives and how actually we use derivatives in machine learning. But essentially what happens is we get the derivative of each value. So here we're using w, but we're going to have m and c. We basically get the derivative and minus it each time till we get to a minimum error. How does this work exactly? Let me go show you down here with the maths. So essentially what we do is we get our error function, which is this. We partial differentiate this with respect to m. And if you don't understand what partial differentiation is, I've added some information in the docs. Once you do all the derivation, you get this little function. And so essentially what this is what you're going to be minusing from the previous value to keep going down and down. Because essentially we're always iteratively looping over our function. And this is with respect to c, that's with respect to m. So obviously, once we get this, we know that the sum of all the values gives you that. We want to reduce that to just the individual values of I. And so we say, hey, the error with respect to m per value is defined as that, hxi minus yi. And the error with respect to c is defined as xi bracket hxi minus yi. Next, we actually want to update our parameters. How that actually works is we've got our next value of m, right? Previous value of m, and we've got this. So we go, hey, minus the previous value by L times the partial differentiation. This is an extra partial differentiation, forget about that. Okay, so what does this actually do? So each time we multiply it by that, or each time we subtract it by that, it reduces it until it gets to the global minimum. And once we get to that global minimum, or get as close as we can, we essentially reduce the error as a whole. And if we reduce the error, that means our m and c values are at their optimum. All right, that might be a lot of, that might be a bit confusing. I've left some formulas here. I've left some actual Medium articles that I've had read over myself, and they're really good in explaining it. So what we're basically having here is like, hey, the next C value is going to be the previous C value minus that, and the next m value is going to be the previous m value minus L times that. Now we can do this however many times we want to do it. We normally call it the training time, so we might run this training program 100,000 times, and it'll keep doing this until it gets a global minimum. This is for the more advanced mathematically aligned people, is kind of like a matrix form I made up. So it's the matrix of M and C equals the matrix of previous C minus the learning rate times the derivative of the error matrix, which I just call phi here. Okay, so now that we've actually explained, or I guess tried to explain a bit of it, if you have any questions, definitely ask me in the comments. We're actually going to try to build this. All right, guys, let's go ahead. Okay, welcome back, guys. Let's just go to our chart.js system that we've built last time. And now let's actually write our code. So first up, we're going to actually go with our error function. And this will actually be the error squared function. All right, let me try to explain this a bit more. So what we have here is the cost function. We normally call it the cost function because it's costing us something. You can understand as the error function. So what we have is our var val cost, and this is our total value. We loop through all the data points, and we define that up here. And so data points are how many x and y values we have. And we basically say, hey, add that to 0.5 to the val cost and go 0.5 times math power gradient times xi plus adder. Adder here is our y-intercept, so it's our c in this case, gradient is our m. We minus that from the actual y and we square that. As our viewers can actually see, if you go back to our code, this is essentially just creating this little mathematical function. All right, next let's just simply create our level 1 error function. And as you can see, it's the same thing as the cost function, but we basically, instead of squaring, just do it to the power of 1. So now that we've got that done, let's actually create our derivatives. Okay, let me explain this code a bit more. So essentially we start off with the gradient, and or the derivative of the gradient as 0. We set off as the derivative of the adder as 0, and then we do this loop. Essentially what we're trying to get is we're trying to just recreate this. All right, so we're just going to go straight to this part. We're trying to do these two parts, okay? How exactly we do it, let me explain it a bit more. So we loop through all the data points, which is the length, and we basically go, hey, the gradient multiplied the ith value of x plus adder minus the yth value of I. And then we do the similar thing, gradient times x value of I plus adder minus y, but we multiply it by x, the ith value of x. As you can see in our code, that's how our gradient actually is set up. So we've got that one, and we've got that one. So let's go ahead and now actually create something so we can update our params. Okay, so what we actually did there is, once again, I want to always keep up with the maths, because all our coding is based on those maths, is we just recreated this literal 2 lines here. So what we did is we said, hey, whatever the gradient is, multiply that by the learning rate and minus it from the current gradient that we have, which we got from our actual params. And we have our adder, and we do a similar thing. We use derive 0 there because the grad is there. We use derive 1 there because the add is there, and we simply return that too. Now, the reason I've set up these functions is it makes it a lot more easier to understand what's happening, and it makes the code flow a lot better. So now we can actually develop our linear regression and take advantage of how we set up our functions. Okay, so let me explain this a bit better. Let me get rid of that. I think that's an error. So what we have here is we got our actual linear regression function. So we start with a random number in between 1 to 10, or 0 to 10, random number in between 0 to 10, and then we loop that this function down here 1,000 times, or whatever your training rate is. So we go update params, and we actually, as you know, that actually updates our params using our x values, y values, and then we set our adder to be total set 0 because this, and we set our gradient to be total set 1 of this. Now, if you look at this closely, what it will do is we'll start with a random gradient and a random adder. It will update the param, so we'll do the gradient descent once, and then it will say, hey, that's your new adder, that's your new gradient. Then it'll do the gradient descent twice, and remember our adder and gradient change, so it's closer to the minimum value. And each time it keeps running until it gets to that minimum we're trying to get at, which is down here, hypothetically. Now, I have something called the learning rate, and I think I haven't explained it a bit clearly. The learning rate is kind of how much each step is, right? So you might go giant steps, or you might go small steps, and by making it too large, you basically overshoot the minimum. And so our learning rate actually depends heavily on what we're trying to get at, and you might need to do the train more depending on your learning rate. And our learning rates are values often between 0.001 and 0.001. It all depends on your training rate. You should also play around with that to get your optimum learning rate. But now that we have our linear regression, we want to actually create some data points from this. So let's next create our data points. Okay, so let me explain this code a bit more. So this has the actual y-intercept as the gradient. This is our mean error. This is our mean squared. That just uses the cost function and the level 1 cost. Here is our actual linear regression. So this is what our final code actually does. So we got our linear regress. So this does the linear regression and gets us the adder value and the gradient. And we basically, similar to our y values and x values up here, we simply create a bunch of regress values using the gradient and the adder, so we multiply it. Now that that's done, we actually can just put this into our planet chart data, and that will essentially give us our regression values. So this is our actual values. This is our linear regression values, so we'll go regress values. Finally, we want to actually export all this data that we're using. So let's go ahead and do that. Okay, as you can see, we're actually getting errors here because we haven't set our training data and learning rate. So let's go back up here and create variables for that. Okay, that sets both constants, and that's going to actually be used in our update param system, since variables are, or const here, are actually global. So finally we export that, and I think that's all done for the chart.js system. So let's go ahead to our data page. Okay, so all we really have to do in our data page is just add a few things. So what I'm going to do is I'm actually just going to copy the code I've already written from GitHub. It should be linked in the description. I'll be right back. Okay, so the link in the description should bring you here. So just go ahead to go to our, actually let's go back, go to our commit section. And yeah, I forgot to commit, so got that. Just search up data page.view, should be the second one. Go here, view file, and gets really good with doing a lot of things. So just go Control A, Control C, and just paste it here. All we've really changed here is a few stuff that I'll explain. So let's go Control A, Control V again. So now I think this is wrong though, because we're using chart.js. Yeah, should we just chart.js? We do that there. Okay, so all we have is a data table that we're doing here. We've imported all our data, and we're just using that inside our data table. This is a Vuetify object. I've linked to the description of Vuetify so you can learn about it a bit more, but all it really is just the displaying of a little table. We haven't done anything else. Our planet chart data is still used down here, and all the stuff is still there. All right, so let's go ahead and run this and see how it works. Okay, guys, we have an error here, and that's probably because we wrote a little code error. So let's go back up to our chart.js and go to our regress here. I think we just did a double bracket there. You're not supposed to have that there, but let's go there. This should take some time, but yeah, I've already rerun it. We've got a nan. Now this is due to not configuring your variables correctly, so it kind of overshot the value you wanted it to be. So let's go up. I've already found a really good configuration, and let's actually place those values in. Now, we've got our linear regression system here working. So as you can see, it's this is the calculated value. So it's 3.00246 blah, blah, blah. If we did that even more, we'd get it closer. And our value 6 is off by like 0.2, so our C value is off by more. Our mean squared error is pretty low. It's like 0.33, so 30, I don't know, like less than 30%. Our mean error, as you can see, is negative, and that's just expected. And I just want to show you that that's negative, and that stuffs up our actual linear regression system. Learning rate 0.01, training levels 99,700. Now, you might be confused and say, hey, what the hell just happened? Basically, you need to configure your learning rate, your training level, and actually your actual formula so they all balance, and it gives you the best linear regression system. Otherwise, what will happen is you keep getting an offshoot, or you get the data points not getting to the correct point. Obviously, this can be changed through automating that, and that's what we'll do a week or 2 weeks into the future. But let's actually see what we got from this. So as you can see, we got our actual values 159. We got our actual values 165 there, and our linear regression 164. But you can kind of see it's really close together. Even if I zoom in, it's not offset by much, and the lines kind of get to the point that we need it to do. Now, as you can see, this is not data points. So what we're going to be doing soon in our next video is we're going to actually add Excel files or CSV files, so we can use data and analyze it through our view system, and it tells us all this extra information we have here. But other than that, I think we're all done here. If you got any questions, hit me up in the comments. As always, hit that subscribe button, that like button if you like this. And if you hated this, send me a personal message saying, fuck you. But yeah, have a good day.